go. All right. Welcome to a special seminar which will be given by Yingshun Sun. He started here about 2 years ago, but maybe I should rewind a little bit. His undergraduate degree is from the Ocean University of China at Qingdao. I don't know how to say it. Qingdao.
Yeah, Qingdao.
And it's on the coast, so it's right on the ocean. I think one of the mottos is it accepts all streams, or all streams flow into the ocean, something kind of unifying like that. Maybe there are 40,000 students, 4,000 professors, similar size to here. I think in his application he said he was interested in photography, and so he actually got into this field through photography, which may be a little unusual. He thought, oh, ocean sciences? No, I'll take atmospheric sciences as a major. I can study clouds and maybe go up on the top of mountains and take pictures. But he went on top of this mountain, and it didn't work out because it was totally foggy. No pictures that day. And he thought, well, maybe I better learn how meteorology works and so I can take proper pictures. And he has won a few awards for some of his photographs, like I think a twin tornado even. His artistry does show up in his science artwork, as you'll see in a few minutes. It's very elegant and appealing artwork, I would say. But he professes to not really know much about math and physics. Well, you can be the judge of that. I don't think that's true at all. But so he's interested in outdoor photography, hiking, even snowboarding. And so one day I thought, okay, I'll go snowboard. I was skiing, but it was a very icy day, and I'm sort of scared of ice. And he totally kicked my ass. So you can ask him any hard question you want.
All right, thank you, Professor Yingshun. And this is the photo after I studied meteorology. So I was like way above the fog that I can take a very nice picture. Today I want to talk about the research I did in the past 3 semesters, and it's a study of QBO phase screening methods and their sensitivity with respect to the northern hemisphere subtropical jet. And here's the outline. First, a brief introduction of QBO and the 3 binding methods I'm using, and then it's all my results and the conclusions and possible future studies. First part, the introduction of the QBO. So QBO is short for quasi-biennial oscillation. It's a tropical lower stratospheric zonal wind variation that propagates downwards about 1 kilometer per month, and with an average period about 28 months. And here's the brief history of QBO. It was first announced by R.G. Reed and R.A. Abden at the AMS in 1960. And the first numerical model that tries to resolve this QBO came up in 1968 by Wallace and Houghton. They only have planetary waves in the model, and apparently there was not enough forcing. The actual forcing is about 2 to 4 times larger than the model's result. In the same year, Listen and Houghton came up with another model with gravity waves. And these show that the vertically propagating gravity waves could provide the forcing needed. And the ongoing research about QBO is mostly about QBO's connection to atmospheric phenomena and try to explain the mechanism behind the QBO. And this is a brief introduction of the mechanism. So QBO is in the tropics. First is the convection in the tropical troposphere, and the convections generate a broad spectrum of waves, short waves like gravity waves, inertial gravity waves, and also the planetary scale waves, Kelvin waves, Rossby waves. And all those waves propagate into the stratosphere, transporting easterly and westerly zonal momentum, and that's what's driving the QBO phase change. And there are 3 routes for QBO influence at the Earth's surface. There are the polar route, the blue arrows, and the subtropical route, the purple, and the tropical route. And I'm interested in the subtropical route. Here is the mirror 2 monthly mean zonal wind data. This can show you horizontal view of the QBO. You can see the phase changes with time. And also the westerly and easterlies, they have a amplitude, like the amplitude of QBO is approximately Gaussian about the equator at a with about 12.5 degrees. This is the vertical structure of QBO. This is the Singapore Sound data. And you can see the westerlies last longer than easterlies. And another feature is like the transition between the two phases. Here, when it's transitioning from easterly to westerly, the transition is more regular and more rapid. And the transition between westerly and easterly is not that regular. It's very different in each cycle, and also it lasts longer. Also, there are two interesting features over here. This is a abnormal cycle when the QBO is not propagating downwards, it's going upward. And also over here, 2000, there's another strange cycle. To define the QBO, there are a lot of indices. First, people use the Singapore Sound winds at 30, 50. If it's a westerly wind, then it's a QBO westerly. If it's a easterly wind, it's QBO easterly. But the Singapore winds only starts in 1978. If you want to go further back in time, you need to get two other stations. Those are the Canton Island and again Maldives Islands. Same, like 30 hectopascal, 50 hectopascal. Later, people start to use the zonally average winds over the equator, not just the stations. And the CDS reanalysis data from NOAA, they use this 30 or 50 hectopascal zonally average winds over the equator. And then later, people start to use meridionally average data. So that's the zonal mean, zonal wind at 50 millibar, average between 5 south and 5 north, or other people use maybe 10 south to 10 north. Then there are also another method to define QBO is use the UF analysis and project all the data on the first two EOFs and define the phase angles to define westerly and easterlies. And I'm using the zonal mean, zonal wind at 50 millibar, average between 5 south and 5 north, because I want to have a smoother data, and also I don't want to go too far from the equator. And this is how QBO affect the Earth's circulation. And this is the most studied phenomenon, is the Halton and Tan correlation. It tells us the relationship between QBO physics and polar vortex and NAO. This NAO is like a surface expression for polar vortex. And during QBO westerlies, the polar vortex is more stable, they're stronger. During QBO easterlies, there are more sudden warmings. Also, people study the QBO and how to make better predictions for MJO. MJO is more coherent and stronger in the QBO easterly phase than in the westerly phase. And also, several different QBO indices are inherently less noisy and thus more predictable in winter in the QBO easterlies than QBO westerlies. And because QBO is the wind structure in the stratosphere, so that can relate to vertical wind shear, and vertical wind shear can destroy hurricanes. So that's also an area of interest in the studies. So during QBO westerlies, we already have a stronger wind shear. That means less hurricanes. When we see in the QBO easterly phase, then we have a weaker wind shear and tends to have more hurricanes. But it's very different in each basins. In the Atlantic, like over the ocean, it's mostly easterly winds. That's when we have a QBO westerly, it can offset the easterly wind. Then in the QBO westerly phase, we have more hurricanes in the Atlantic. And also, the QBO wind arches downward into the subtropical troposphere. This is a map made by Yingshun et al. in 2021. This is the wind temperature normally, and this is the wind. You see the westerlies here bend downward, arches downward, and forming a horseshoe shape, and also the easterlies here bending downward into so here it bends downward, arches down to the subtropical troposphere. And because of this bend, and there should be some secondary meridional circulation over here, which is related to the temperature anomalies, and that's also my interest, the QBO and the zonally average meridional secondary circulation. For the subtropical jet, the zonally is kind of hard to define where it is according to latitude because it's wavy and sometimes it has superpositions like the subtropical jet and the polar jet, they can merge together. So I use the zonally average center to see where it is, and it's located between 30 to 40 degrees latitude, and it moves with the sun. Like in the northern summer, the subtropical jet moves northward, and in the winter it moves back south. So this is the secondary circulation. When we have a westerly shear, then we have downward motion in the equator and is offset by the upward motion in the subtropical area. So when we have a easterly shear, then we have rising at the equator and sinking at the subtropical area. And the rising and sinking at the equator is offset by the circulation of the equator. And because of the normally upward motion, downward motion, we could have a anomalous temperature. This would be a anomalous cooling, and this is a warming. Then according to the thermal wind balance, we can know how the zonal wind changes with height. So let's assume the subtropical jet is right over here. Then the dt dy, like this is a cooling effect, the dt dy would be negative. So on the right hand side is a positive term. Then on the left hand side, this will be a positive term. And that means we will, if the subtropical jet is right over here, then this pattern can enhance the subtropical jet. But if it's on the other side, it will be the opposite case. Now the data method, the data I'm using is the ERE5 area analysis data, multi-mean zonal wind with the resolution of quarter degrees from 1979 to 2021. And the QBO index I'm using is a zonal mean zonal wind at 50 hectopascal average between 5 south and 5 north, and I call that QBO 50. The UF method, I also use the zonal mean zonal wind average between 5 south and 5 north, and I take 7 levels from 100 hectopascal to 7 hectopascal. Then the 3 mini methods. The first one is mostly used, people define westerlies and easterlies with a certain threshold of wind speed. So how do we define the wind speed? So you choose a certain wind speed, like maybe above positive 5 is westerly, below negative 5 is easterly. Or you can use the standard deviation, like if it's away, 1 standard deviation away from the average, it can be defined as westerly or easterly. Or it's like the percentage. The first 33% can be the westerly, the last 33% can be defined as easterlies. And here are the 2 data sets. So this is the average zonal wind at 70 hectopascal. This is at 50. And we're using 50 because you can see at 70 the westerly winds are very noisy. It's very wavy. It's kind of hard to define where the transition is. But for the 50 is so much better. It's clear to see like this is transition from westerly to easterly, and here's easterly to westerly. So the 50 millibar wind is better than the 70s. And for the second method, the 4-phase method, we already defined westerlies and easterlies. So want to define the other 2 phases, like the transition from westerly to easterly, and the transition from easterly to westerly. So here, when it's transitioning from westerly to easterlies, we can see there's a easterly shear. The easterly wind increases with height, and when it's transitioning from easterly to westerly, you can see the westerly wind increases in height. So this is westerly shear. So the transition from westerly to easterly is defined as easterly shear, and the transition from easterly to westerly is defined as the westerly shear. And the rule to define those transitions is like they have to be in between a westerly and a easterly, and sometimes they have some fluctuations, and we have to take out the fluctuations. And the blues are the westerly shears, and the blues are the westerly shears. The red are the easterly shears. And this is at 50 hectopascal, and I choose +5 and -5 as the threshold. So above 5, they're all westerlies. Below 5, these are all easterlies. And the red over here is the transition from westerly to easterly, blue easterly to westerly. And when I use 5 to 5, you can see almost all the data are in the 4 phases. But when I increase the threshold, like spread the threshold to 7 and -7, there are some fluctuations over here. I can't define these because I define when it's above 7, it should be westerlies. When it's below 7, it should be below -7, it should be easterlies. Over here, these cannot be defined in any of the phases. So if I want to increase the bin size in the 2 shears, I will lose a lot of data. That's one of the reasons why I'm using the 5 and -5 to define the 4 phases. And the third method is the EOF method. Wallace came up with that. And here are the 2 leading EOFs. The first EOF is the blue, the second EOF is the red. And the first EOF has a 0.98 correlation with the 10 hectopascal zonal wind minus 70 hectopascal zonal wind. So it's like the shear from here to there. And the second EOF has a 0.98 correlation with the 30 hectopascal zonal wind here. And the first EOF can explain 49.6% of the data. The second EOF can explain 30%. So they all together can explain 80%. And if I project all the data on the 2 EOFs, here is the scatter plot of all those data. And we can see over here, the density is pretty high. This is the highest density. And over here, the density is very small. This is one feature I noticed. And maybe I want to do more study to see like why this is the case like this. And if I connect all the dots according to time, it will be this second graph over here. It's kind of noisy. Then I take the 5-month running mean to make this smoother, figure out all the high frequency data. You see it's going round and round. It's like a strange tractor, the Rossler tractor. But there are 2 cycles that are like all those can be the turbulence, but these 2, there are definitely some force in driving them to be acting like this, the 2 cycles. And this shows how the vertical wind changes with the phase angles. So over here, the phase angle is 0, 30, 60, 90. So at first, when 0 is in the westerly phase, if we define QBO at 50, and 30 is still, easterly phase, and in 30 is still easterly. In 60 degree, it becomes the westerly shear. And right after this one, 30 degree later, it becomes easterly. So you can see this shear is pretty short, happens pretty fast, the transition from easterly to westerly. And all these are westerlies until over here, finally we can see the easterly shear phase, and then it go back to easterly phase. So you can see the easterlies are a lot more than the westerlies are a lot more than the easterlies. Also, the transition from easterly to westerly is faster than from westerly to easterly. Okay, my results. I did a sensitivity test on the four-phase method and the UF method, and plotted the meridional section of zonal mean, time mean, zonal wind, and normally of that. And also I did because the subtropical jet changes with season, so I also did a seasonal meridional section of those two variables. And the vertical wind structure in different bands in the two different methods. So for the sensitivity test, I used this point to test the sensitivity when I change the threshold in those two methods. Like for the four-phase method, I changed the threshold like 5, -5, or 5 negatives, all those. And with respect to the subtropical jet, 30 north to 100 hectopascal. For the four-phase method, I changed these two thresholds and do all the combinations like 5, -7, -5, 7, and here is the result. This is the QBO 50. When I define QBO at 50 hectopascal, and this is when I define QBO in 70 hectopascal. And you can see the whole domain, like the smallest value is like over here, about 1.1. The largest value is over here, or about 3.5. And in the whole domain, the difference between the largest and the smallest is within 2 meters per second. So the sensitivity is not too large for the 50 hectopascal index. If you use 70, it's going to be very different, because the easterly winds, they're not too wavy, there are not too many noise. So we can see if we only change the easterly threshold, the sensitivity is kind of small, like all those contours are almost parallel to the x-axis. But if we change the westerly threshold, the sensitivity is pretty large. Like the contours are pretty packed. When we change the westerly threshold, the subtropical jet can change a lot. And also because I want to test the sensitivity on both westerlies and easterlies, so that's why all those data are the QBO, the zonal wind, time mean, zonal wind in the QBO westerly phase minus the QBO easterly phase. That's why those numbers are small, not as strong as the subtropical jet. So this is the reason, another reason why I'm not using the QBO 70 index, because I want small sensitivity to make my result more persuasive. So I don't use the 70. And to test the sensitivity for the UF method, first I need to define where should be the westerlies and where should be the easterlies. So these two colors are under the QBO 50 index. When it's positive, then it's green. So these are all the westerly winds. And the orange here means the wind is negative, so it's all easterly over here. And I plotted a line to separate these two. This is like a zero wind. And on one side, it's all defined as phase 1, which is the westerly wind. On the other side is all phase 2, the easterly wind. And I draw another line perpendicular to this to find the center of this phase. So it's 150 for westerly and 330 for easterly. Then, after I find the center, I use different width to define the 4 phases. So over here, all the phases are 90-degree width in each. Like the phase angle is 90 degree for each phase. And this is the westerly, over here is the easterly, and here's the transition from westerly to easterly, and this is the transition from easterly to westerly. And I changed the angle. So this is when the phase angle for westerly and easterly are 120, and the phase angle for the transitions are 60. Now, if I change all those phase angles, you can see most of the domain, the sensitivity is kind of small, It's pretty similar to the four-phase method. The smallest value here is about 1.6. The largest, like when it is not the phase angle of the QBO westerly and easterlies are not smaller than 110. The largest value is about like 3, so it's not that different. But when we try to make 4 equal-sized bands, like for the westerly and easterly bands, they're 100 degree or 90 degree. The sensitivity can be pretty huge, like on these 2 boundaries. To compare that with the 4-phase method, you see, as long as we're not trying to make 4 equal-sized bands, the sensitivity with respect to the subtropical jet is small. So that's after the sensitivity test. This is how I define the 4 different phases in each method. Now the green means the westerly phase for the 4-phase method. So it's QBO west, and the orange here are the QBO east, also the 4-phase method. And the yellow dots are the transition from westerly to easterly, so they are the easterly shear. And over there, the red dots, they are the westerly shear. And so QBO westerly, QBO W is defined as when the zonal wind at 50 hectopascal is above positive 5 meters per second. And the QBO easterly shear is the transition from westerly to easterly. And QBO easterly shear is the zonal wind at 50 hectopascal, smaller than negative 5 meters per second. The QBO westerly shear is the transition from easterly to westerly. For the UF method, these 4 are the 4 phases. So this is phase 1, P1. This is phase 2, P2, phase 3, P3, and phase 4, P4. And the phase angle, the width of this phase angle is 140 degree for those westerly and easterlies, and 40 degree for the transitions. And in this case, I can have similar sizes in both methods, so I can compare the results of these 2 methods later. Here are those variables I'm looking at. This U bar is time mean, zonal wind. U bar prime is the departure from time mean, zonal wind, normally. And U bar QBO W means the time mean, zonal wind in the QBO westerly beam. And U bar prime QBO W is the time mean, zonal wind in the QBO westerly phase minus the time mean, zonal wind. This is the meridianal section of U bar in the 4-phase method. And you can see over here in the tropics, this pattern is descending with the 4 phases, like in the QBO W, the easterlies over westerlies, and in QBO E shear is descending, and QBO easterlies is westerly over easterlies, and in the shear, this pattern goes down again, and then it's another cycle back to this. And the little plot over here shows the wind speed at this point, 30 north, 100 hectopascal. It's how the subtropical jet changes with the 4 phases. But we can see those features in the tropics very clearly on these 2 plots. But if we want to look at what's happening in the subtropics, it's kind of hard to see because they look all similar. That's why I take the average out to see the anomalies. So here are the anomalies for the 4-phase method. You see the horseshoe shape is not so obvious when we are using the 4-phase method. Like it's only it's more here in the northern hemisphere than the southern hemisphere in the westerly phase and easterly phase. So clearly there's a horseshoe shape here. And the strongest signal for the subtropical jet is in the westerly shear, in the easterly shear. Over here, you see the signal is not as strong in the QBO westerly phase or in the easterly phase. So the strongest signal is in the easterly shear phase. And this is the meridional plot for the UF method, also the U bar. You can also see the same thing, this pattern descent with phases, and also not much to see in the subtropics. So that's why I also, and also this is the subtropical jet in the 4 phases. Is very different from the 4-phase method. When we use the UF method, the speed just decreases with time, with phase. And we take the average out. The UF method shows the better horseshoe shape patterns in the westerlies and easterlies. And also the strongest signal is also in the shear bands, like the transitions. It's not in the easterly shear anymore. Now it's in the westerly shear. Like the strongest signal of the subtropical jet is right in the westerly shear, P4, phase 4, in the UF method. And if we want to take a look at the difference between the 2 methods, these are the four plots for each phase, and it's the difference between UF method and the 4-phase method. For the westerly and the easterlies, the signal at the subtropical jet is not strong, but when it comes to the shear, this is pretty strong. So when we want to talk about how the QBO affect the subtropical area, it's very important to know which method we're using, because these can generate very different results. Like over here, these are the 2 westerly and easterly bands. The signal is pretty small, but when it comes to those shears, the difference is pretty large. And then I want to take a look at in each season, what is the difference between the 2 methods and what is the difference in the subtropical area. And this is the mean field for the 4 seasons. You can see the subtropical jet moves northward to about 40° north, and it moves back in winter to 30° north. So for the seasons, I will just put those anomaly plots here. This is when I apply the 4-phase method in the QBO westerly band. You can see the signal of the subtropical area is pretty small in all 4 seasons. So for the QBO westerly phase, there's not much seasonality in this phase. And now we come to the easterly shear phase. So over here, the subtropical area, the signal is a little stronger than the westerly phase, but still is not noticeable. Like over here, it's only 2 meters per second difference, so it's not that strong. Now we come to the easterlies. Again, the signal is pretty weak in the subtropical area. Like we can't really tell if the season can change the pattern in the subtropics. So the interesting thing happens when we look at the westerly shear in the QBO, when the transition from easterly to westerlies. So in March, April, May, June, July, August, the signal is still small. But in September, October, November, this area, like in the northern hemisphere, subtropical jet has a very strong signal over here. So in the autumn, it seems the QBO shear can decrease the subtropical jet here. And in the winter, there's a dipole pattern in the northern hemisphere. I think this is the reason for the subtropical jet, the southward movement when it is winter, the subtropical jet moves southward. It's not because of QBO. And this is for the EOF method. We apply the EOF method for the phase 1, also the westerly phase. The signal is not strong over all seasons. And when we go to the transition, from westerly to easterly, the signal in the subtropical jet area, northern hemisphere, is not strong as well. And we go to easterlies, also the signal is not strong, it's almost zero. And another interesting thing happened when we go to the phase 4, when it's transitioning from westerly to easterlies, the signal is pretty strong. But in the 4-phase method, the strongest signal is in September, October, November in this plot. And now when we apply the EOF method, the strongest signal is in the spring, March, April, May. And the shape of this pattern is almost the same as the 4-phase method in autumn. And in winter, we also have this dipole over here. Now, if we take a look at the difference between the two methods. So this is the EOF method minus the 4-phase method. So in the westerly phase, the two methods are almost the same in the subtropics in 4 seasons. In the easterly shear, we have a difference in northern hemisphere summer. Like the UF method is weaker here. For the easterly phase, also not much stuff going on, but the most interesting thing is when we go to westerly shear, this is the difference between the two methods. Like in the UF method, this has the negative signal over here. In the 4-phase method, the negative pattern is right over there. So we can see the difference between them. And another interesting thing is that in the winter, the two methods are exactly the same. They picked exactly the same 5 months in winter. And let's take a look at the wind structure. This is the 4-phase method. The most interesting feature for the vertical structure is in the QBO easterly shear. It's almost all the composites are packed over here, showing the easterly shear. But there are a few places over here, like the shear between 30 to 50 is almost 0, but they have a easterly shear higher above. Like they look similar to the QBO easterly phase, but just at 50, the wind is not defined as easterly. They have pretty weak easterly winds at 50. And if you go to the EOF method, the vertical structure, they're more consistent, but for the 50 hectopascal, P1 should be the westerly phase, but we can still see some easterly winds in the westerly phase, and also in the easterly phase is kind of noisy as well, but we can see westerly winds in the easterly phase. And now for the UF method, we don't have those high shears anymore. It's all easterly shear here from 50 to 20. Now, if I take show the difference of the spread of these two methods, the red shadings are the EOF methods, and the gray shadings are the 4-phase methods. So we define the EOF with QBO 50. So for the gray shadings, The spread under 50 hectopascal is apparently smaller than the spread of the green is apparently smaller than red in all the 4 phases. But above 50, the gray spread, like the gray spread more than the red. So when we look at the wind above 50 hectopascal, the UF method, they're more like together, less spread, and they're telling the same story here. Okay. Sorry. And finally, this would be my conclusions and the possible future studies. So my conclusion is, first one is QBO 50 is a good index to look into when we apply the 4-phase method. And the threshold we choose for the 4-phase method and the phase angle for EOF method, the sensitivity with respect to northern hemisphere subtropical jet is small overall, but high on the boundaries. And we will look at the subtropical jet. The 2 methods have noticeable differences, especially in the 2 transition beams. And the subtropical jet changes more with seasons in the 2 transition beams, like in westerly or easterlies, it don't change that much. And the largest difference between the 2 methods is in the transition from westerly to easterly beam in spring and fall, March, April, May, and September, October, November. But the vertical wind structure in the 2 transition phases is different in the 2 methods. For the 4-phase method, it has less spread below 50 hectopascal. For the UF method, it has less spread above 50 hectopascal. And here are some future studies in my mind. First, I need to do the statistical test for all my results. And also, I want to plot the temperature anomalies, meridional sections, just the same as my wind meridional sections. If I have that and the wind, I can take a closer look at the secondary meridional circulation associated with QBO and its influence on the northern hemisphere subtropical jet. And after that, I also want to take a look, take another time-dependent variable into account, like take a look at the solar cycle, El Nino, and to see how, like people already studied about those, how they interact with westerlies and easterlies. And now I want to see how they interact with the transition beams. And the last one would be study the reason, like why applying the UF method, somewhere the spread is like pretty dense. We have the highest density at about 135, and at about 30 degrees phase speed, the spread of those dots is very large. All right, that would be all. Thank you.
Maybe you'd like to ask the people. Just before you go, I wanted to say nobody's ever studied all 4 phases of the QBO. This is the first time. People usually just do east minus west. Starting from that, easterly and westerly are not linearly inverse. They're not negatives of each other. And nobody's ever studied down to 50% of this information. And that he achieved a union between the EOF method. He chose just the right phase angles so you could do the first intercomparison. All right, so better say that because you might not assert that.
Thank you. Okay. Any questions? Yes.
When you were talking about the sensitivities, and you were using words like it was a small difference, right? And that was anywhere from like a 1.5 meters per second to a few meters per second.
Yeah.
But when you looked at the actual differences in the strength of the jet between the different phases, my first impression was sometimes it was on that same order of magnitude. Did I misinterpret that? Like, what do you consider a small sensitivity and large, and is it based on how the subtropical jet actually changes between those phases? I got a little bit confused about those different magnitudes.
Yeah, that's a good question. So, like between 1 and 2 is kind of small, but according to my results, especially the season plot for phase 4, the signal can be as strong as more than 5 meters per second. So I consider that as a strong signal. When it's like 5 or 4.
Is that strong because that's about the order of magnitude that the jet actually would change between the different transition periods? I think I just wanted to make sure I understand those magnitudes.
Yeah.
Yeah.
Let me show how the jet changes. So over here, this is how the jet changed
So that's
according
about-
to the phases.
Yeah, okay.
And
So that's around 4 or 5 meters per second. And so
Yeah.
okay. So
Yeah.
so 1 or 2 you don't consider that large because it's
No.
much smaller than that.
yeah. Also, this is for the EOF method. It changes
Yeah.
like at an order of 4 to 5.
Okay, that helps. Okay. Thank you.
Evan?
Yeah, this is all really cool. I have like 3 questions. I'll try to just keep it to one. Okay, so when you do the 2 EOFs, you showed like that visual center, like that center of mass, and then you proceed to draw all of your angles from the origin instead of from that center of mass. Do you
Yeah.
think like if you chose the angles to be from there,
Mhm.
would you be able to split them up more closely to the 4-phase method?
Yeah.
And then the second part of that is you're saying the transition zones are narrower than when the actual phases themselves. Is there any reason to limit yourself to just 2 different sizes for the phases versus letting all 4 of them be however large or small they need to be? Because I think you qualitatively said that the easterly to westerly transition happens on a shorter time scale than the westerly to easterly. So maybe those phase angles could be different.
Yeah. So you can see like this is the transition from easterly to westerly.
Yeah.
They're more spread, so that's
Yeah.
why if I choose the same angle, still these have a smaller size.
Yeah.
Yeah. And also why I'm not moving everything to the center is because I think this is the original data. If I move to that, that means I'm putting a putting a westerly. This is like the easterly. I'm putting a easterly value in all those data, so I'm changing the data. A lot of people do that to move the center to the visual center and do the phase angles, and I just want to use the original data instead of put another value in there.
Yeah.
Yeah. It's like if I move everything here, then I need to minus EOF 2, like minus this.
I guess my counter to that would be if you're changing the phase angles anyways and not using like 90 degrees, then essentially like, somewhere on that circle, you can pick different phase angles to hit the same spot. So maybe it doesn't matter.
Yeah. Yeah, I can also do a sensitivity
Yeah.
test for like moving things around.
Okay.
Amy? Yes.
I have a question. Along those lines, did you take out the mean zone mean one at the equator in calculating the EOFs? Since there's a background easterly.
Yeah.
Okay.
I took away the mean.
Okay, I was just wondering if that would account for the shift. And then my other question was, when you were doing the composites and you were thinking about the seasonality of the transitions happen really fast and they tend to be kind of linked to the seasonal cycle. So I'm wondering how many actual different seasons are represented in the composites, or whether or not they're just like 2 seasons and they happen to be El Nino years.
Yeah, that's a very good question. So the problem is that we don't have that much data. So especially in the westerly shear, so there's only like 30 to 40 data in total. So it's like 5 to 10 or just about 10. So we don't have that many data in each month, especially in the winter. For this transition, we only have 5 months here. So that's a good point. Like I have to take a closer look to take away all the other variables. But when I take them away, I have even less data. Then I don't think it will be convincing. So that's a problem. If I have more data, and I think I can solve the problem.
That's a good idea to try to focus on the April transition. That usually comes down preferentially.
Yes, Jared.
How well does ERA5 actually simulate the QBO compared to observations, and why do you use that versus another reanalysis?
The reason I'm using that is just Professor Fishman used those data before, and I just want to use the same data set. Yeah. And I think I'm not 100% sure on this, but the observations between reanalysis data and the observations are pretty similar, but the observations are like only one station at Singapore, and the reanalysis, like I never compared the reanalysis data at Singapore with the observation, but I compared like the equatorial mean with the Singapore. They're not so different. Especially when it's like above 70 hectopascal, they're more similar. Yes, Dan?
Why there's such a difference in the time scale of the transition? Say westerly, easterly versus easterly to westerly?
Sorry, I couldn't hear that really well.
Why is there such a difference in the duration of the transition from westerly to easterly compared to easterly to westerly?
Oh, that's a good question. So I want to show. This is a part of the reason. We have a westerly wind above. So this is the westerly transition, and we have a downward secondary circulation, and this can help the whole pattern move faster. And over here, when it's a easterly shear, this is like an upward motion. It can slow down the transition. Yes, ma'am.
Could you go to the slide where you compare your 4 quadrants methods to the EOS method?
Yes.
I really enjoyed that plot.
This.
Yeah. Is the third quadrant your westerly shear phase? That one?
Yeah. Yeah.
So that's the one where you were seeing the differences between like March, April, May, and September, October.
Oh, that was this
Was that
easterly
okay?
shear. Yeah.
Okay. Okay.
It's one of the reasons why they're so different is because this phase has the least data.
Yeah.
So
you
it
just don't
can
have
be
a lot
very
of
different.
points.
See,
Okay.
if I use the UF method, it has like orange, green, and red. If I use the 4-phase method, it's just all red. So I think that's the reason why it's the most different.
And maybe this would just be fun to see because you're looking at seasonality anyways. But if you colored all those points by seasonality and compared it, would it be completely random, or would there be some coherent structure to when the QBO is in a certain phase seasonally?
Yeah, that's very interesting. Yeah, I'll do that.
I think that would be cool to see. And this is I really like this way of visualizing it where you're doing this comparison.
Thank you. And also, I think there's another interesting feature. Is like there's no point over here.
Yeah.
It's pretty. I don't know what's going on here. Why there's
Well,
nothing.
That amazing circle makes me want to do more planetary science, where you just like go away from the noise, and it's just so nice.
Well, I guess if there aren't any other questions, please consider talking with Yingshun in the future about all this stuff, and let's thank him for a very nice.